So the key point I'm trying to make is, instead of propagating the carry this way, I am going to now propagate the carry this way. I don't have to add the carry immediately to the left, and that's what even he was saying, you can add the carry later. Though it's not a functionality problem, it turns out it's only a delay optimization that we get. Okay, this is what I'm going to do. Right? So now let's start filling out what should be my, half adder, full adder. First row, all are only half adder because it's only the partial products. The two ands I'm going to add, that's all, right? Therefore, this is a half adder, half adder, half adder. What about the last one? Just one, and actually I can even bypass that, go and add it to the next bit. I can bring this guy sort of here. I will not do it for now. Okay, I'll keep this as a half adder for now. You will see the reason why. So I'm going to call it a half adder and ground the other input. Okay, what about the next stage? Of course, now where should the sum come? The sum propagation has to be again like this, correct? One way to check what you're doing is correct or not, remember I said that when you're trying to find zk, it has to be all the xi, yj such that I plus j is k. So if you are, for example, you get z0, z1, z2. In z2, you should add only what? x0, y2, x1, y1 and x2, y0. Because the sum should always be, so that is an easy check for you. Make sure that that is being propagated correctly. So you have x1, y1 coming here. This is, maybe x1, y1, x2, y0, and this one is what? x0, y2. So it makes sense. Okay, these are simple ways to check that your answer is, you're doing the right thing. So now, second row, what are they? All full adders. Third row. Yeah? Okay. Actually, you can make it a half adder if you're so keen. Yes, definitely, you can make it a half adder. Right? Now, clearly, I have not taken into account those carry outs of my last row. The sum has gone past, right? I can't say this is Z3, for example, because now the carry has got propagated downward, right? So is this Z3? Z3 is fine, you're right. So the other guys, is this Z4? Yeah, why? Because the previous carry I have not added now, right? So the same carry propagation is going to happen like this, and therefore I need to add more full adder blocks here. Yeah. Okay. Hold on. It's not that easy because this guy will now give me a carry. The last stage, now I'm down to the last stage. I can't do anything. I have to propagate the carry sidewards. I can't delay it anymore, right? So these guys will give me a carry. This will give me a carry. Okay? So therefore, yes, maybe this can be like what? A half adder. This has to be a full adder, right? What about the carry out from this stage? I have not yet accounted for that, right? So therefore I need to put one more what? Half adder here, and I will get a carry out here. It turns out this last stage will give me all the sum bits, will give me Z4, Z5, Z6, Z7. C out can be discarded because we have now done extra adders we have put in, right? That C out is basically just, you can discard it if it's unsigned multiplication. Any questions here? How will C out come? No. In the previous implementation, the array multiplier, Z7 was the C out of the last adder. Here Z7 is the sum bit of the last adder. Correct? Unfortunately, I have drawn it badly. So, yes, sorry, Z4, Z5, Z6, Z7. Right? Any questions? Oh, what will happen to that carry out? Why will carry out always be 0? Correct. Yeah. Correct. You are absolutely right. This is what I said. You can take this product and simply plug it here. Right? No. Yeah. And therefore I get rid of that block, and actually instead of propagating to the carry, I am going to propagate that directly. That this bit is 0. Right? So the output of this block will be what? Oh, no. Sorry. You're wrong. I'm wrong. This guy itself would have been X3, Y1. Similarly, this X3, Y2 would have come here. Correct? And thereby we would have avoided few more adders. You're right. But I'll show you why I'm not doing that. Okay, I'm going to retain this as it is. Okay? Yeah. How am I sure that C out will not matter? No, you're right. I know. So, yeah, what he's saying is effectively, yeah. So I think what they're saying is right. C out will always be 0, because if you propagate this X3, Y1 down and remove that half adder, you can basically remove this set of half adders, man. That's the idea. That's what they're saying, because the other input to those half adders are 0. Right? See, this input is 0, this input is 0, and so is this input, which means the sum is just one of the inputs. No, wait. One of the bits is 0, right? X3, Y0, there is no carry in here. Correct? I am removing all this. So that means that half adder is just going to take the partial product and pass it through. You agree with me? It will just go through. So this x3 y0 will appear here. This guy will appear here. This guy will appear here. And this guy will appear here. That's all. So if you propagate it like that, you will find that final C out is redundant. Okay. But the reason I am retaining this is you will see in the next 10 minutes or so. Okay. Any other questions on the carry save multiplier? Just the construction, right? Now we will go ahead and do this critical path analysis. Okay. So now let's do the same exercise. T and equals 1, T sum equals 1, T carry equals 1. Just for an example here. So let's now put the arrival times. Output of all AND gates is 1 arrival time. So this will be 1, 1, 1, 1, 1, 1, right? This will also be 1. Okay. Now, what about the first row? When will the sum be ready? Z1, 2. When will the carry be ready? 2. Right? This guy, what's the arrival time? 2. This is also 2. This also is 2. Now, next stage. This Z2 will arrive at 3. This is 3. What about this guy? You are going to select between max arrival time, which is 2, 1, 2. So the max arrival time is 2 plus another unit time, you get 3. And then Z3 will be ready at 4. Right? Now, what about the output of this guy? Here, 4. Previous guy, I mean the next one, 4, 4, 4. Correct? What about the sum? This guy, 4, 4, 4. So now we are going to propagate it to that final adder, which is basically a ripple adder. Right? So when will Z4 be ready? 5, Z5, 6, 7, 8. Right? Now I'll ask you, what is the critical path for this? Simply take the highest guy, then track the next, sorry, not this guy. You come here, oh, okay, we have to write that arrival time also. If 5, 5, 6, 7, then simply track this, sorry. This will be my critical path. Right? You go up, it can't be this, right? 3 is here, and then you basically pick this guy and then come here. Right? So the critical path now gets very well defined like this. One path is clearly longer than the other paths. Which path? Yeah, from here you can even go here. You mean this way, right? Yeah, so it turns out these two paths are the same. The delay will be the same. Effectively, if you want to write the delay of this path, carry save, it's going to be T and plus how many things to propagate down? Why empty carry? I am asking only till here. till the input to that ripple adder finally. M minus 1 T sum plus the final stage is called a vector merge stage. This guy is vector merge. Okay, now observe what happens there. The inputs to this final adder stage, all of them arrive at the same time. You see, all the arrival times are 4, 4, 4, 4, 4. So it's like basically a ripple adder where all the inputs are arriving at the same time. So therefore, the final stage you can speed up by making it some other adder, carry save, a carry select or a carry skip or even a carry look ahead adder, right? So we'll simply call this as T merge delay. Now this, depending on what architecture of adder you choose, it will be O of n or O of n minus 1. If it's a ripple adder, then this will simply be n minus 1 T sum plus T carry. Right? So you will find in your project when you implement this and implement a ripple adder, you will get some delay. If you replace this with a carry look ahead adder, you will gain a lot of time because this T merge delay is as much as this delay. You look at the numbers, n minus 1 T carry plus T sum, T and plus m minus 1 T sum, they are very, very similar numbers. So therefore, that final addition is on the critical path. So that's why it doesn't even matter whether I came along this path or this path, because ultimately from there you are going to the T merge, vector merge array anyway, right? That was your question, right? Why I chose this path and not. I'm saying it doesn't matter because I'm now going to T merge after that. Okay. So with this you will find that you are able to optimize the multiplier very well.